So good morning everybody. So let's start with some topic on digital design. What did we see during our yesterday's class? We have seen some Boolean laws, right? So what is the use of those Boolean laws while simplifying your Boolean equation? Okay. So I have already shared some of the videos which will be based on next few sessions. Just watch that, okay? Okay, duality. What is duality? See, you have Boolean equation, right? You have Boolean equation. You have Boolean operators. What is the Boolean operators? Tell me. Not, and, or, right? So, you can interchange. In place of not, you put, in place of and, you put or, in place of or, you put and, okay? So, in such cases, sometimes your Boolean equation relation does not change. It's called duality. In place of and, you put or, in place of or, you put and. Such relations also valid. It's called duality. Have you understood this? Okay, I'm talking about duality. Okay, see, for some example we will take. I said in place of and you put or, in place of or you put and, in place of 0 you make 1, in place of 1 you put 0. That's called duality. Examples, check here, a dot a plus b, a dot a plus b. You just see this is an and operator and you have an or operator here. See here, this is your and operator and this is your or operator. Now what you do? In this place you put plus and here you put dot. What are you going to get? You're going to get a only, yes or no? Right. See here, a dot a, simplify this. Can you simplify this? A dot a into a dot b, right? That is going to be your, right? You get a plus ab once again, right? You b you take outside, right? See, a dot a plus b, right? Now you see here, okay, this is b, right? Just take a outside, you have 1 plus b, this is going to be 1, yeah, this is a, okay? Similarly, here also you have a into a plus ab, correct? You are going to get a, right? Duality worked out here. Duality has worked out, right? Have you understood this? Duality, okay? Now see here, a dot a bar is equal to 0, right? Now in this case, you see a plus a bar. What is a plus a bar? This one. This relation holds good, okay? Similarly here, a into 1 is equal to a plus 0 is equal to a. Similarly, ab whole bar, this is nothing but your De Morgan's theorem. There is no much importance for this. Wherever it is required, you can make use of this, okay? Now, there are two important things I am going to mention here while representing your Boolean function, right? Now, at this point, you must have understood what is a Boolean function, right? What is a Boolean function? Or what is Boolean equation, right? If I have an equation, right, something like, say, I say f is equal to abc plus a bar bc plus a b bar c, so this is nothing but a Boolean equation. This is nothing but a Boolean equation, or it can be called as Boolean function. Both Either you say Boolean function, Boolean equation, whatever it is. Okay. Now, this Boolean function can be represented in two ways. Listen carefully. Sum of products or same equation can also be represented as products of sum. How does it look like? See, name itself indicates sum of products. You have products and its sum. If the Boolean function is represented, okay, as a sum of products, then it is called as SOP form. Now see this equation. I have an equation, Boolean equation, f of a, b, c. See, what's the meaning of if I just put f in the bracket a, b, c? That means that particular Boolean function has got only 3 Boolean variables, right? Entire equation should have only 3 Boolean variables. Suppose if there is a, comma, b, comma, c, comma, d in that, then that equation will have 4 Boolean variables. Okay. Now see this equation, it is given as ABC plus a bar into b into c. Is it not product, sum of product? This is product, right? ABC is a product, a bar bc is a product, and you sum it. And it is this form of your Boolean function or Boolean equation is called as sum of product form. Right. Now, next one, product of sum. You will have sum in one entity, and then you have product of. You have a sum and its product. See here, see this particular equation, right? See, you have the sum here, right? And its product, see, it's a product of sum. These two are sums. These two are sums. And this is the product. Hence it is called as product of sum. And here it is sum of products. This is the product. This is the product. This is the product. This is the product and its sum. So we call it the sum of products. These two are two forms of your Boolean function. Remember this, okay? Now let us see another term. We have something called min terms and max terms. Okay, see this two form of representation of Boolean function, either in sum of products or products of sum, we will have the term, right? Can you see it has these terms? Can you see this is one product term, right? This is another product term, right? Similarly, can you see this? What is this? This is one sum term. This is one sum term. And those terms are actually taken as a product here. It is taken as a sum here. Have you understood this? There is a specific name given to this. These terms, okay, in this sum of products is called as min terms, right? In this product of sum, this is called max terms. Have understood this, okay? So here in sum of products, it can also be called as sum of min terms, sum of min terms. Here we can call this as product of max terms, max terms. These are given names, these terms are given names. Have you understood this? Okay, that's what I'm going to come here. I have changed my variables here. Instead of a, b, I have x and y here. Okay, so my equation f will have only two variables. My equation will have only two variables, right? So what are the four combinations of x and y possible now? There are four combinations of x and y possible, right? What are those things? It is xy, x, y bar, x bar y, x bar y bar. I can have an equation which can be combinations of all these 4 terms, right? Right? So these terms are called as min terms. Okay, now because see x bar y bar, it represents complements, right? So this is actually like 0 0, right? Corresponding min term is called as m0. Similarly, you have this 0 1, right? 0 1, that is x bar y, right? This corresponding min term is m1. Now xy bar corresponding min term is m2. xy corresponding min term is m3. Suppose I have an equation, okay, xy plus x bar y. Consider an equation f of x comma y is equal to xy. Can you write this in terms of min terms? It is equal to m3 plus m1, right? Normally you can put it in an ascending order. It can be written as m1 plus m3, that's all. Have you understood this? Okay. Though it is used to represent your sum of products. If at all your Boolean equation is represented in sum of products, that means it is a sum of min terms, that's all. Right? It can be 2 variable or it can be 3 variable. Can you tell me how many min terms will come for 3 variable? 8. 4 variable you will have 16. Understood? Okay?
So does the order matter?
Doesn't matter, okay, no problem. Of course, it starts from m0 to m7. For the 3 variable, suppose I have a 3 variable, your x bar, y bar, z bar will be m0, right? Now see 0 0 0 0 0 1 z. This is your m1. Similarly, x, y, z is going to be your m7. That's all.
So sir, for the notation for x, like it's supposed to be m not for x bar, y bar, z bar.
Exactly, it's supposed to be m not only. Because you have, see this bar denotes 0 0 0. That's why this m not will come. This is very important. This order is very important. You cannot do say x, y, z as m naught. You cannot do that. X bar, y bar, z bar will be m naught. That 0 0 0, 0 0 1, 0 1 0 notation you have to follow while doing that. Have you understood this?
Sir, so in this example, it's just sum of products. That's why it's called a min term.
Exactly.
But if it
That product term is called as min term. This is the product term, right? X bar, y bar is a product term, right? So that is a min term. So sum of product is sum of min terms. That's all. That's why I told you this product term in sum of products has given a name and we call it as a min term, right? Now let us see what is max terms. This is for 3 variable. I told this is for 3 variable, okay? 3 variable. Max terms, right? See here, max term, suppose if you have it in the product form. Suppose if you have it in the product form. See here. Here notation is little different from the min terms, right? See, we take, see, there it is product, right? Min term is for the product. Max term is for the sum, right? So like you have xy, this is the min term. What is this? X plus y is the max term, right? Have you understood this? Now listen carefully. Now listen carefully. See, x plus y is written as max term m0. Here the order is reverse. Order is reverse, right? Now see, x bar plus y bar is m3. X plus y bar is m1. X bar plus y is m2, capital M2, and x bar plus y bar is equal to capital M3. Remember this. The order in max term is the reverse of the order in the min term, right? See what we did here in min term, Suppose I have x bar, y bar, x bar y, x y bar, and then x bar y bar. So what I did, I wrote small m, m0, m1, m2, sorry, m2 and m3, okay. This is for min term, I said product. Similarly, I can have sum also, right? It can be say x bar plus y bar, x bar plus y, listen carefully here, okay, x plus y bar, then x plus y, right? See here, these are max terms, but order reverse. So this will be your m0, this will be your m1, right? This will be m2, this will be your m3. Understood this? Okay? This is very important to remember. Okay. Similarly, you will have for 3 variable, right? Same, reverse, ulta, put it from bottom, that's all. Your max terms will come from the bottom. If you remember min terms, max term you can easily remember, right? You know this, I have told you, you know this. This is min terms, min terms. Max terms in this case, you instead of, that is for product, so sum, this was sum. This is for product, this was sum. So in place, plus will come, plus will come, plus will come here. But when you put this min terms, that term, it will go from, this will be m0, this will be, this will be m0, this will be xy, right? This will be xy, it's not x bar, y bar, okay. This will be m0, m1, m2, m3. Understood about min term and max term, okay? So I have already shared you my video, you can just watch if you have. Can you tell me what is the purpose of having this min term and max terms? It is just to simplify your, equation. See, suppose if you have a big equation, suppose assume that you have 4 variable Boolean function, right? 4 variable Boolean function, right? Just see how much time it takes for me to write a equation of the form a b c d bar plus a b c d plus a bar b bar c d plus a bar b bar c bar d bar plus a bar b c plus a b c d bar plus, and so on. I have a big equation. So see, it takes a lot of time, or remember this. Instead of that, you just write the min terms. I have understood this. Just write the min terms. That's enough. Right. Now see here, I have an equation here, remember, which is given as m1, m4, m7. m1, m4, m7. Assume 3 variable. Can you tell me what is this exactly? Of course, it is sum of products only, right? There's no doubt about it, right? But tell me, what is the actual equation? What is m1? Right? What is m1? See, what is this one? Tell me. X bar, y bar, z bar is equal to m0, right? This is x bar, y bar, z bar. What is this? X bar, y bar, z. You know how to do this, right? Okay. Now this is going to be your m1, right? And what is m1? X bar, y bar, z. So this is your x bar, y bar, z plus, right? So min term 4, this one, x, y bar, z bar plus x, y bar, z bar plus Then you have M7. M7 is this one. X, Y, Z. X, Y, Z. Understood? Right? Similar way you can write max terms also. This is where you use your max terms and min terms. Can you see this equation? What is M0, M1, M2, M4? Can you just write equivalent equation? This is going to be x plus y plus z, right? You can just write it. This is about your min terms and max terms, okay? So just remember these concepts. Now see here, you have an equation, see, a bar plus b bar, this is your equation. A bar plus b bar is your equation, right? Now how do you represent it in the form of min term and max term? Because there is only one term there, right? In that case what you do, see, suppose if you multiply this with the b plus b bar, it is not going to change its form, right? What is b plus b bar? 1 only, right? So for this a, for a bar, see here is given, for a bar, multiply this a bar with b plus b bar. Now it is in the form of 2 variables, right? 2 variables. Now similarly, there is only one variable here. If you want to get 2 variables, see, unless you have 2 variables, how do you represent it using min terms? To represent min terms, you need 2 variables, right? Yes or no? That's why what you do, multiply this with a plus a bar. What is a plus a bar? A plus a bar is 1, right? Right? So now you write it. Multiply. A bar b bar, b bar a, this is a bar a b bar, a bar b bar. Now, any simplification possible here? This is possible, right? A bar b bar, a bar b bar. What is a bar b bar plus a bar b bar? A bar b bar only, right? So now you will have a bar b, a b bar and a bar b bar, okay? Now what is this, tell me? This is M1, right? M1, what is this? This is M2, what is this? M0, see here, it's written as M1 plus M2 plus M3. There is one more form to represent this, it's called canonical form. Suppose the same equation can be represented as summation of m of 0, 1, 2. What is the meaning of this? Meaning of this is equal to m0 plus m1 plus m2. See how easily I can represent my Boolean equation, right? Instead of writing a equation like this, right, I am going to write my same Boolean equation in this form. This is called as canonical form of representing your Boolean equation. It's an easy form, right? That's the purpose we use this, okay. So max term will be in M3, okay. Now, of course, this is already in the form of max term, right? A bar, B bar, right? You can just put it as M3, doesn't matter. It's already in the max term, max form, okay? Fine. Now say this. Let a function be represented by f1 is equal to xy plus y bar plus x bar yz bar. This is neither in min terms nor in max terms, okay? I'm in class. Fine. Now see, take this equation, right? How can you implement that using basic gates? You can do it, right? Right. All of you understood this. This is a Boolean equation. Now, this is your corresponding logic diagram. It's quite easy. See, there is a AND operation here, there is a NOT operation here, and there are and not operations here. Right, it is very easy to draw this diagram, right? It's very easy to draw this diagram, okay? See, first and this, x and y are the inputs, x and y are the inputs. It's the best way to draw like this, draw this is better, you have a inputs. There are three variables, right? This is x input, y input, z input. First, x and y has to be ANDed. This is your AND gate. Take one connection, put a dot here from x, put it here, take a dot here, put it here. So what you are going to get here is x, y. I'm just explaining you. Now, after that, y bar. This is y, right? Put it here. Put one not gate here, y bar. Okay? Then what you have is x bar, y, z bar. X bar, y, z bar, three input AND gate. And before that, you have to not x and z. Okay, take x, not it. Okay, and y direct, and take z, not it. Okay, and what you do, you AND it, then you just have to OR all the three gates, just OR. This is what your F1 is, that's all. Now, I will give you an homework, right? Can you implement all these gates in universal gate? Right? I will give you one homework, okay? I'll give you one homework. How do you convert all this gate using only universal gates, that is 2 input NAND gate? Can you implement this using only 2 input gates? This is 3 input gates, this is 3 input gates, right? Can you implement this using only 2 input gates? How do you change? Suppose, assume that 3 input AND gate, 3 input OR gates are not available. Exactly. So instead of this, what you do? You use how many gates? 2 gates. These 2 input will go here, take the output of this and give it to another OR gate, and then take this input here, that's all. Similarly here, take those 2 inputs and take this here and put it here, this is your output. This is what going to this another input. Right. Now, how do you change this? How do you change this to have only universal gates? To have only universal gates. Right. One way of doing that is you replace every gate with its equivalent NAND gate. Its equivalent NAND gate. See here, for example, what is this AND gate, right? What is AND equivalent of NAND? Exactly. I will replace this with instead of this gate, what I will do? I will put a NAND gate, equivalent NAND gate, which is this one, right? Yes or no? Yes or no? Now, can you tell me what is the equivalent of this? What is the NAND equivalent of NOT gate? I have done this in my last class, remember that. Don't forget. Every class you need to remember. What is the NAND equivalent of NOT? Same thing here, right? So this is replaced by this. I have replaced this gate, I have replaced this gate. I can replace this gate also, right? So now I will replace this gate with an AND. This also I will replace with an AND. Right? Now I can replace this also with the NAND, right? I can replace this also with the NAND. Can do that homework. After you do this connections with the replacement, some gates may be redundant. Where you will get the redundant, I will tell you. See, you replace it first. First you replace every gate. You know that, right? I told you, how do you replace a 2 input OR gate with a NAND gate? See here, listen carefully, listen carefully. See, this is 3 input, this is your OR, right? See here, this you are going to give it to another gate. You are going to take this. This is what actually your 2 input. This is 3 input OR gate, but assume that 3 input OR gate is not available. You are going to implement it with the 2 input OR gate. Right? Okay. Now, can you replace it with the NAND gate? Come on, I have done this in the last class. Big table I have done. Okay, can you replace this with the NAND gate? I will take this A, B, C, okay, F, okay. Now see here, this is your A, listen carefully. What is this, tell me? What is this corresponds to? What is this corresponds to? This corresponds to this gate A, right? Gate G1, right? Okay, can you replace this? Same thing, same thing. You will have one more OR gate. This output will go here, and this is your B, and C will come here, right? What is this corresponds to? This is another gate, G2. This is your G2, this is your G1. Understood this? Now, this I have done for simple circuit. Sometimes you may come across with situation that when you have multiple gates connected, definitely you will come across with a situation something like this. Now you tell me the answer. Do I have to keep this? You may come across with this while you replace every gates with the NAND gates, right? Assume that these two are coming in series. When these two are coming in series, do we need to keep that? Why we don't need to keep that? Redundant, right? Why? Because if you give 0 here, 1 will come, right? And that 1 will go here, 0 will come. So do we need this 2 gates? Not required. Remove the redundant gates. After replacing every gates by universal gates. This sit and practice. Right? This is the OR gate, and this is same OR gate only implemented using NAND gate. Have you understood this? So given a circuit, right? Now, see, normally what will happen is you will be given a circuit like this. Your circuit will be in the basic gate only. This circuit, or else you will be given this statement. Okay? You will be given this statement. You will be asked to simplify the statement first. Okay? You can use the Karnoff map, which I am going to take it now to simplify this. Okay? This equation may not be in the simplified form. This equation may not be in simplified form. You can reduce that equation to minimum number of literals. What is the meaning of minimum number of literals? You can have minimum number of min terms. You can reduce it, right? So that your gates can be reduced if you want to simplify this equation, right? That's why your question may be given an equation like that, simplify it and implement it using only universal gate. So what you have to do at that time? First you have to simplify this. You can draw corresponding logic diagram using basic gates, which is very easy, right? After that, replace every gates by its equivalent universal gates. Once you do that, you look for a redundant gates, remove that, okay? Do it in pencil. All this operation, do it in pencil. Right? Because when you have redundant gates, if you draw it in pen, you will not be able to remove that. That's why do it in pencil. Then you get a final logic diagram for this. Have understood this? Okay? See this. See this. There's another equation. Right? You have x into y bar plus z into x bar plus y plus z bar. Okay? This equation now you don't know whether it is a min term or max term. You don't know because both are there in that. Okay. In such, can you just implement it using only basic gates? Try this. Don't look into this. You do it yourself. And after that, replace this every gate by NAND gates. Anyway, I'm just asking you to replace this every gate by NAND gate. Every gates you replace by NAND gate. Right? I'm just going to draw. This is your NOT gate using NAND. Okay? This is your this is your AND gate using NAND. This is AND gate, this is NOT gate, this is AND gate, and what is OR gate? OR gate is this one. Replace every gate with these gates. Then remove the redundant gates. This is your OR gates, OR gate. Okay, so can you do that? Replace every gate, replace every gate. Do it in, if possible, do it in pencil. It's very easy. You just have to replace every gate with the corresponding NAND gate, that's all. Be careful with the connections. Then remove the redundant gates. I told you what are the redundant gates. To answer your numbers, Aditya single, absent. Sania, Stalin John, Yusra Hakim, Jania Suresh, Jins Abraham, Christina Mary George, Alekia Pandit, Laksha Malik, present, okay. Joseph, Naitra Chedda, absent. Ali Hussain Syed, Diya Vinu, absent. Parina Kalpesh, okay. Advait Maheshwar, Aditya Nandakumar, Pranav Murthy, Ritvik, Riyan, Zobia, Sri Niketan Iyer, Muhammad Eman, absent. Shokat Siddiqui, absent. Manasvi Gandhi, Muhammad Farhan, Arun Satish, Mutina Jayant, absent. Aditya, Diorurkar Aditya, absent. Keshav Bansal, Nishit Piyush, Jayesh, Sara Amit, Aditya Agarwal, Anirvin Jain, Ajay Kumar, absent. Paparti, absent. Ashwin Kumar, absent, so many absents. Rohan, absent. Rohil Harish, absent. Rushiraj Singh, okay. Pratham Naveen, Tanir, Pawan, Bansari Pawan, Manas, Rakshit, Bharat Gupta, Nikhil, Aishwarya absent. Arvind James, Aditya Sunoj, and Rachel, Stephen Joseph Alex, Amin Binu, Marwa Jalil, Harshavardhan, Cyril Joseph, Isha, Reshma Reddy, Sanabar, Harun, Sagar, absent. Adit, absent. Nandana, absent. Aditi, present. Calder Savio. I think all of you know about attendance policies, right? Okay. Inform your mates also. Okay, did you complete this? Did you get any redundant gates? Right? Okay, fine. I have already done this. What is this, tell me? Using NAND, right? Basic gates using NAND gates. Okay? Similarly, what is this, tell me? Basic gates using NOR gates. I already done that for you. Okay? F is equal to AB plus CD. Implement it using only NAND gates, right? Implement it using only NAND gates. How do you get this? The two redundant gates will go, right? So you will remain with this. You understood? To realize a logic diagram which has basic gates using universal gates. Right? See, this is AB plus CD. This is A plus B into C plus D. See, this is implemented like this. Yes or no? It has got two OR gates and one AND gate. Replace this with the NAND gate. Replace this with the NAND gates. Okay? And after that, replace this also with the NAND gate. See, here there are two gates, right? See, this is also possible. Okay. If you implement it using only NAND gate, you get different one, right? If you implement this using only NAND gate, you will not get this. You get something different. Right? Universal gate. This is called universal gates. NOR and NAND is called as universal gates. See, your questions may be asked in different way. Listen carefully. You may be asked to implement it using only NAND gates. In that case, do you try to insert NOR gate into that? No, right? Don't do that. Right? Suppose if the question says use only universal gates, you have an option to either use NOR gate or NAND gate. Have you understood this? Okay, accordingly you do it. It's left to you, right? If you use only NAND gate is also fine. If you use only NOR gate is also fine. If you mix NAND or NOR is also fine in that case. Fine? Okay? Sorry. So let's go forward. This is, what is this? To implement a Boolean function. You can implement any Boolean function using Verilog, right? If I ask you to implement this Boolean function using Verilog, okay, you can either choose any one of the model and write the program, right? Now you can choose a data flow model here. Suppose if you are using data flow model here, see, how do you write? Assign y is equal to, where are you going? Assign y is equal to, what is this? A and B and C, right? Then you have a OR operation. You can put this inside the bracket. Then A and B operation, okay? Then OR A and C. This is what you are going to write, right? Of course, all these things you know, module name, and all these are ports. You have ABCR inputs and output is Y, then assign like this, right? Now I will give you a small work. Can you write a gate level model for this? Gate level model.
So what's the difference between data and gate?
Which one?
Data and gate.
This is data flow model. You should have practiced little more. I already covered this. See, this is called a data flow model. See, data is flowing here. See, whenever you use assign, okay, this is a data flow model. Gate level model means you use gates. So you use one AND gate here, right? This is gate 1, AND gate, right? And you use another AND gate. You use another AND gate here, right? And then you use all this with another gate 4, which is OR gate, right? Have understood this? So now what you do? First is your AND G1, okay? You have to use wire, right? Output of this will come in W1, output of this will come in W2, output of this will come in W3, right? Right. So now this will be W1 A comma B comma C, okay? Now you have another AND gate, which is, this is called gate level model, where I use the gate here. G2 W2 comma A comma B. Then you will have another AND gate, which is called as G3 W3 A comma C. Then you will have OR gate, which is G4, which will take the inputs from W1, okay, output is Y. Output is Y. First you will write the output. In gate level model, first you write the output. Then comma, W1 comma, W2 comma, W3. This is called as gate level model, where you use the gates. This is gate level model. Once again, go and watch the videos which I shared you on Verilog. Every time we will not repeat in the class. Structural model you can use, if any one model if you ask, you can use structural model. You can use mix match of all codes, structural model. Yes. See, your structural model is something like this. I'll just tell you. Wait. Right? See, this structural model is, see, there is no much difference between structural model and behavioral model. Sorry, gate level model. It's the same one, right? Yes. You can do that, no problem. Okay.